Okay, welcome back, everybody. Last lecture basically tidied up everything that we wanted to finish talking about before moving on to kind of the next big topic. The next big topic that requires us to start thinking about analytic functions as power series. And since we haven't talked about a complex power series, well, we have to develop that, right? So the goal now, so the immediate goal now is to begin to think of analytic functions as, we'll say f of z, as complex power series, i.e., we define, or we think of f of z as being equal to some power series that looks like this, okay, for some coefficients a sub n. Okay, so these are like power series that you're used to, from Calc 2, or real power series, where instead of a z back then you had an x. And of course, you might remember that there was all kinds of things that went into this, basically, where you could talk about this making sense, right? There were certain windows where this made sense. For some power series, these things were fine everywhere, right? So, for instance, the power series for e to the x was fine everywhere. Its radius of convergence was infinite, right? So that was the term that we used back then, was radius of convergence, which was, basically the radius of the window on which you could talk about this power series making sense. So all of those discussions are going to enter in here in very, very similar way. And so you're actually going to find that this mirrors almost exactly everything about power series that you already knew. And so you can consider this kind of like a review. But before I can get to here, I have to go through the entire definition of these things, right? So, but before I can rigorously write out these things, we have to go through definitions and basics of complex sequences and series. Right? Because that's what you got to do when you are talking about, whenever you want to talk about series, you got to talk about sequences first, because these series only make sense in context of certain sequences having limits, so you have to understand what it means for a sequence to have a limit, and so that's exactly going to be our jumping off point. Okay, and so what is a sequence? So a sequence of complex numbers is literally just a set of complex numbers. So I'm not even going to write out the definition, but a sequence of complex numbers is just a set of complex numbers, right? You might see these, a generic term here might be called the nth term, and typically this is thought of as being indexed by the naturals. Okay, so indexed by the natural numbers. Okay. There's no, there's no reason why the indexing has to work exactly like this, right? Could you have zeroth terms in the sense that, you start at some z sub 0 instead? There's nothing wrong with that. Okay, but this is how we think of a sequence of complex numbers typically. So thinking about them, of course, as points in the plane, it's just a collection of points, right? And I'm not making any claims about these things being all distinct, right? You could take a sequence of complex numbers, it's all just the same complex number. It's literally just, say, 1 plus I over and over and over again, right? Every single term in that sequence is just 1 plus I. And so the sequence is the entire set taken together. A single entry, right? So like z sub 2 on itself is called a term of the sequence. So this would be the second term of the sequence, just like we used this same terminology before. So then, z sub n is the nth term. Okay. So that's what a sequence of complex numbers look like. Of course, before I'm not even going to give examples right now without first just going ahead and talking about the thing we're actually interested in here, of course, which is when you talk about sequences, you want to talk about limits of sequences, right? And so our first definition in this material concerns the limit of a sequence. So what is a limit? A sequence of complex numbers, which we list as z sub 1, z sub 2, and so on, has a limit z, okay, if for all positive numbers epsilon greater than 0, there exists a positive integer that is a natural number n sub naught, such that the modulus of z sub n minus z is strictly less than epsilon if n is strictly greater than n naught. Okay, so here's my epsilon definition of limit of a sequence. What is the picture, of course? Well, the idea here is that I have some terms in my sequence. Maybe this is what's going on. Maybe here's z sub 5, so you don't even know what's happening there. Okay, and this is just a random collection of points in the plane. But if these things have a limit, then what will happen eventually is that these things will all be within some ball of radius epsilon centered at z. So here's z, here's my proposed limit. And the idea is that I can pick any epsilon greater than 0 here, and eventually all of the terms of the sequence will lie inside that epsilon ball. Well, just interpret what it is that's going on here, right? So I pick any epsilon greater than 0, then there must exist some n naught that is a positive integer, it's a natural number, such that all terms in the sequence after the z sub n naught term lie in the ball of radius epsilon. But I can pick any epsilon greater than 0, right? So the idea here is that I can squeeze the end of the sequence, right? Of course, the end of the sequence, right? A sequence in general has infinitely many terms. And so we tend to think of the limit as the end, but when I say end in this sense, I'm really talking about like the tail of the sequence. The last, I have a cutoff point, the last infinitely many terms after some cutoff point. So here, the cutoff point I'm talking about is all terms that are described by having their index be greater than this n naught. Okay, and so intuitively, the way we tend to think about this is we want epsilon to be very small. That is, we want to make this arbitrarily small so that all of these last infinitely many terms of the sequence are infinitely close, or are arbitrarily close to this z. And we tend to think of n naught as being, potentially it needs to be large. Okay, so potentially it needs to be large. It might not necessarily be large, but that is, something that we consider as a possibility. And this n naught, of course, might depend on epsilon. Okay, so this n naught might depend on epsilon. So if I choose an epsilon very, very small, I may have to alter this n naught in order to make these terms fit. But this gives rise to the intuition, of course, that it doesn't matter what, say, the first 50 or the first 500 terms in the sequence do. What matters is the last infinitely many terms, right? Which might sound like a ridiculous phrase, but what that means is that look, that ultimately in this picture, it didn't matter what these first few terms did. But of course, because a series has a sequence has infinitely many terms, even if instead of having 5 points, say, outside in this picture, I had 50 points or 500 points or 5,000 points, that's still a finite number of points, and that's ultimately not something I'm going to concern myself with, right? The idea is that what really matters is the tail of the sequence, right? That's where the convergence happens. So in this case, we say that z naught converges to z. So in this case, we say the sequence z sub n converges to z, and write that the limit as n goes to infinity of the sequence z sub n is equal to z. Okay. All right. And so the intuition, I'm a little bit off the screen there. So the intuition here is that these terms in the sequence are getting arbitrarily close to z. Okay, as in once n is sufficiently large, these terms in the sequence are arbitrarily close to z. Okay, if such a limit does not exist, we say the sequence diverges. Okay, so this is terminology that you've heard before. Okay. Now, I'm going to state a theorem that turns this into merely an application of all the stuff you knew about sequences of series from before. So the following helpful theorem ties this to things you already knew about sequences. Right? Because what's the difference right now? Well, in everything you did previously in sequences, you weren't dealing with complex numbers, you were just dealing with sequences of real numbers, right? Okay, and so the following theorem helps relate this to sequences of complex numbers. Okay, and so suppose that we have the sequence z sub n. Okay, and the sequence can be thought of course, once you have complex numbers in a sequence. For each of those complex numbers, you can consider their real and imaginary parts, and say for z sub n, its real part is called x sub n, and its imaginary part is called y sub n. Well, then that defines two sequences of real numbers, right? So n is a natural number here. Okay. Let z be written as x plus iy, then the limit as n goes to infinity of z sub n is equal to z if and only if so this implication goes in both directions. The limits of these real sequences are what you think they should be. So limit as n goes to infinity of x sub n is equal to the real part of the limit, and the limit as n goes to infinity of y sub n is equal to the imaginary part of this limit. Okay, so this is a really handy and nice thing that happens here, because this is just telling you that these limits of complex series are exactly behaving in the way that they should. Okay, so proof here is pretty standard epsilon proof for sequence convergence. So I'm not going to go into it. So if you're interested in that, you can look that up. It's on page 182 in the text. But we're not going to deal too much with the epsilon, the definition of sequence convergence, because we are going to do what you did, all the way back in Calc 2, where you had the definition, but what you ended up using more were properties that you proved about how sequences should behave. And you had various ways that you go about finding limits of sequences. And usually the way you did this was you had the fact that you could treat, even though these sequences technically, right, the indices are only on the natural numbers, and so the things you're plugging in are only on the natural numbers, you made big use of the fact that if you treated them like functions of a real variable, then finding out whether or not those things had limits told you a lot about the sequences themselves. That was typically how you did it all the way back in Calc 2. Okay. All right, and so let's do some examples here to show how this works. So maybe first example, let's let z sub n be the sequence that has real part 1 over n cubed and imaginary part 1. Okay. So z sub n is 1 over n cubed plus I, where n is just some natural number. Okay. So how would I actually show what the limit of this thing is? Well, using this theorem now, if I'm looking at the limit as n goes to infinity of z sub n, if this thing is going to exist, right, then it has to satisfy this fact that I have to be able to find this limit by limiting, taking the limits of these two real sequences. Okay, and so this is the limit as n goes to infinity of x sub n, that's 1 over n cubed, plus I times the limit of the real part here, which is 1, so the limit as n goes to infinity of 1, right? But the limit as n goes to infinity of 1 over n cubed is 0, right? And the limit as n goes to infinity of 1 is just 1, so this is 0 plus I times 1, right? So this is just I. Okay. All right, and of course, that is an example of very, intuitively kind of obvious limit that you can compute. You could do this by definition, but again, that's going to be something we're not going to do that often, just because we're going to very quickly move beyond that to be using some of these properties that we're going to show instead. Okay. All right. And so, let's do another example. Maybe one that's a little bit more complicated here. So let's do another example. Let's let z sub n be equal to minus 2 plus I times minus 1 to the n over n squared. Right? Again, n is a natural number here. Okay. So what does this tell us? Well, if I want to take the limit of this sequence, then this had better be equal to the limit as n goes to infinity of minus 2 plus I times the limit as n goes to infinity of minus 1 to the n over n squared. Right. Well, this is minus 2. The limit as n goes to infinity of this thing. So minus 1 to the n is bouncing back and forth between 1 and minus 1. But of course, this n squared term in the denominator is going to dominate everything. As n is getting huge, it's going to be 1 or minus 1 over a very huge number. And so this is going to be 0, right? So it's minus 2 plus I times 0, so this is just minus 2. Now, you might be happy to stop here and be like, well, we have computed this limit here, right? And we are happy. But let's not stop here. Let's use this example to do something else. So note, if we use polar coordinates here, right? Okay, and so r sub n is, say, the modulus of z sub n, and we take big theta sub n to be the principal argument of z sub n. Okay. All right. Then the limit as n goes to infinity of r sub n is what? So taking the modulus of this, what do I get? So I'm summing the squares of both of these things. Since I'm squaring this, I'm only going to have minus 1 to even power, so that's just going to be 1. Squaring this, that's 1 over n to the 4. So this is the limit as n goes to infinity of the square root of 4 plus 1 over n to the 4th, right? But this limit is easy, so this thing's limiting to 0, right? This is a continuous function where I'm talking about, so I can pull this limit through. So this limit as n goes to infinity of square root of 4. This is just 2. Okay. All right, but what about the limit as n goes to infinity of theta, say, sub 2n, right? And the reason I want to think about this in terms of this subsequence, right? This is called a subsequence here, versus, say, another subsequence where I'm looking at the odd terms here, right? What limit do I get? What's the limit as n goes to infinity of big theta sub 2n? So this is going to be the argument of z sub 2n. When I'm looking at z sub 2n, the power of minus 1 here is always going to be even. So note that the reason we're splitting this, so z sub 2n is equal to what? This is minus 2 plus I times minus 1 to the 2n is 1, so this is 1 over n squared. And z sub 2n minus 1, it's guaranteed to be odd. So this is minus 2 plus I times minus 1 over n squared. Okay. Well, where is this, right? Versus where is this? Okay. If we're taking the limit, right, as n goes to infinity, right, then where are we headed here? So in this case, taking the limit as n goes to infinity of this thing gives me, I'm going to be at minus 2 plus I 0 through positive values. So this thing limits to pi, right? But when I take the limit as n goes to infinity of this thing, going through negative values here, this thing is going to limit to minus pi. Okay. Is this a problem? Yes. This implies that the limit as n goes to infinity of big theta sub n does not exist. Why? If a sequence has a limit, this limit is unique. Okay. And so this means that you can't have a sequence, say, converging to two different values, and so a limit has to be unique here if the sequence itself converges. Okay. All right. So something happening like this as part of its subsequences isn't allowed. Okay. So this is no good. All right. Maybe I should actually state that separately. As a result of topological properties of the complex plane, if limit as n goes to infinity of z sub n exists, then it must be unique. Okay, which just means if there's any other complex number that the sequence limits to, it actually has to be the same, right? So if you show that the same sequence converges to two limits, those two limits have to be equal to each other. Okay, and now we're primarily interested in talking about sequences for the purpose of talking about series and their convergence properties. Okay, and so you need sequences in order to define series. So what is a series? Okay. Well, an infinite series so an infinite series of complex numbers is just a sum of terms in some sequence of complex numbers that we'll call C sub n, right? So C sub n, which will index is going from 1 to infinity. Again, if we have these indices, say, starting at 0 instead, that's not at all a problem, right? You're just adding like a single term to the sequence and rescaling. We'll talk more about maybe the specific concerns we might have over keeping the indices straight a little later. Okay. And so, if we have an infinite series of complex numbers, this is just a sum of terms in some sequence. So this is literally just c sub 1 plus c sub 2 plus c sub 3, and so on. Now, the and so on is entirely the difficulty in series, right? Because if it was truly just a sum, if this is a finite sum, there's nothing to say, right? It's not even a name for that. We just call that a sum. So what is important is that this is an infinite sum. And of course, rather than just writing this all the time, we have the sigma notation to denote this. So this is the sum from n equals 1 to infinity of the terms in the sequence C sub n. Okay. All right. Okay. Now, let's write directly from this the definition of convergence. Because as you might recall, convergence of a series has to do with convergence of a particular sequence that is defined from the series, right? So, strangely enough, we need a sequence to define a series, but then from that series we can define another sequence called the sequence of partial sums, and it's the convergence of that sequence, or the divergence of that sequence, that tells us whether the series that I use to define it is convergent or divergent. Okay, and so a series converges if its sequence of partial sums converges. We'll write this in the following way. A series that I'll write as the sum from n equals 1 to infinity of, say, z sub n. So this is, z sub 1 plus z sub 2 plus z sub 3, and so on. This converges to the sum called S. So we say that the sum of this series is S if the sequence, which is given to us as this big S sub n, which is the partial sum, that is from little n is equal to 1 to big N of z sub n. Now this is a finite sum, right? So z sub 1 plus z sub 2 and so on up to z sub big N. Okay, where big N is some natural number. Okay, if the sequence of partial sums, so the sequence of partial sums is this sequence big S sub n. If the sequence of partial sums converges to S, then whatever that limit is, that is what I say the series converges to. Okay, and when we say that, in this case, we write the sum from n equals 1 to infinity of z sub n is equal to S, whatever that limit is. Now, here's where things get very tricky, right? I'm going to go ahead and spoil fun, although I'm not really spoiling anything because this is something that you had a lot of discussions about in Calc 2, probably, which is to say, how hard is it, right, to sum series typically? The answer to that is very hard, because basically, with a few notable exceptions, in your entire mathematical career, there are exactly two types of series that you are able to sum. Okay, like I said, practically. Those are geometric series and telescoping series. Okay, so geometric series, there is a formula which we will derive that you'll remember for how to deal with geometric series, and I'll remind you what a geometric series is. A telescoping series, that's a descriptive name. A telescoping series telescopes, right? You can think about collapsing an old pull-out telescope, right, onto its ends. The way that telescoping series work is that the telescoping term tells you that all of the middle terms cancel out in some very, very nice fashion, leaving you with only the ends. Okay, and so telescoping series are also, those are nice for us because we can compute with them. Other than that, there's basically no general process for computing these sums, and so even seemingly very simple series can be very hard or impossible to actually compute. Okay, so there's tons of examples here. Okay, so in this case, this limit is unique. Okay, so in this case, this limit is unique. Okay, so the sum is unique. We say it converges to the sum S. We say that this limit is unique. Notice this is a limit of the sequence of partial sums, but we don't use the limit symbol here on this sum. Okay, because that's taken care of by the fact that we're using the limit here on the sequence of partial sums. Okay, if this doesn't exist, right? If the sequence of partial sums diverges, then we say this sum diverges or this series diverges. So if this doesn't happen, we say the series diverges. Okay. All right. So that's how this goes. Now, there's a nice theorem here. Okay, there's a nice theorem that is very similar to the one that we had for sequences. So what does this nice theorem say? So suppose that Z sub n is a sequence that has real and imaginary parts x sub n and y sub n respectively. N written in this way is always some natural number index, and let big S be big X plus I times big Y. Okay, then this convergence of this series, so the sum from n equals 1 to infinity of Z sub n, this is equal to S. Okay, so this sums to S if and only if the sum of the real parts, right, sums to big X, and the series defined from the imaginary part sums to the imaginary part of the sum. Okay, and so we have an analogous thing here, just like we had for sequences for complex series. Okay, and so I'm not going to go through the proof of this, so proof left to reader. Okay, but this tells us, among other things, immediately that if I have this series and I've written, say, this series in this way, okay, then I can do this. So there's going to be words that I write after this, okay? Do not, whatever you do, don't box this in and then don't pay attention to the words I write later. Okay, so this is equal to the series involving the real parts, right, plus I times the series involving the imaginary parts whenever the left-hand side converges or whenever both series on the right converge. Okay, so if there is divergence here, say if the left, if say one of the sums on the right diverges, or if one of the series, or if the series on the left diverges, then you can't do this splitting. You can't write it like this. Okay. But if you know that you have convergence, then you can actually write it like this. And so now the main purpose of this theorem, so main purpose of star is just like the corresponding fact about sequences. It's to show us that a lot of the properties that we knew already from calculus for sequences and series hold here. Is to show that many of our facts about sequences and series from calculus carry over here. Okay. Okay. All right, so what's some of these facts? So here are some of these facts. Okay, this is not an exhaustive list, but here's a few important ones. Okay. So one, all of these can be viewed as corollaries of that theorem. So here's the first corollary of that theorem. If a series sum from n equals 1 to infinity of z sub n converges, then the sequence z sub n defining these limits to 0. Okay. Note, converse is false. Okay. So converse is false if the limit of the terms in the series, if these limit to 0, that does not tell you that the series itself converges. So there were plenty counterexamples of that coming to you from calculus, from Calc 2 already. But this is just not enough to actually say that that's what happens. If you want like a simple example of what it is that goes on here, basically you can take something that limits to 0 and slap a -1 to the n on it, and in many cases that is going to yield a nice counterexample to this fact. Also, there's actually, no, better than that, because actually a lot of times that would, a lot of times that can actually make it converge. So rather than do that, you can consider something like the harmonic series, right? So the sum from n equals 1 to infinity of 1 over n. as an example. And of course, we have to consider things like this, right? So take harmonic series, because they are technically series involving complex numbers. So take harmonic series, right? The sum from n equals 1 to infinity of 1 over n. All right, this, so the limit as n goes to infinity of 1 over n is 0, but the series diverges. Okay. Okay. So typically the way that this fact is used then is to actually show that a series that you suspect doesn't converge, well, doesn't converge because, or it provides a quick test, okay, that you can call the, this was the nth term test, is usually the name for it in Calc 2. Okay. So the nth term test is the thing that is a quick check. Checking it and it being satisfied because this converse is false doesn't tell you that a series converges. But if you go to check the nth term test and see that this sequence doesn't limit to 0, then it has no hope of converging. Okay. Why is this corollary, like, why does this work? Right? Well, because we actually know this nth term test from Calc 2, right? And so this has to be true coming to us from Calc 2. And so the proof of this is really quick. So sum from n equals 1 and z sub n is the sum from n equals 1 to infinity of x sub n plus I times the sum from n equals 1 to infinity of y sub n. We can write it like this because we know that both of these, so if we assume that this thing converges, right, then this left-hand side converges, so we can write this series split in this way, okay, by that thing that I boxed here. Let me just go ahead. There we go. So whenever the left-hand side converges, which is what we're assuming here, okay, then I can write this series split in this way. The second I do this, well, this converges. I know that these two things have to converge, but these are series involving real numbers only. Okay, and they converge. And so what does this mean? By the nth term test from Calc 2, right, it means that since these converge, the limit of x sub n as n goes to infinity is 0, and the limit as n goes to infinity of y sub n is 0. And this is from the nth term test from Calc 2. Okay, and thus the limit as n goes to infinity of z sub n is 0 plus I times 0, right? So it's just 0, and that's it. Okay, that's how we can use the theorem to show that. Okay. All right, so here's another fact that follows immediately from this one. So second fact is that the terms of a convergent series are bounded. So the terms of a convergent series are bounded. How do I get that? What's another way of stating this? i.e., when the sum from n equals 1 to infinity of z sub n converges, then there exists some positive constant m such that the modulus of z sub n is less than or equal to m for all n. So here's what is meant by this statement. Okay. Okay. Why does this imply that? Well, these terms are limiting to 0, right? Okay, so the idea here is I can pick, right, uh, a large value of n here, and the last infinitely many of these terms in the sequence lie very close to 0. And so only finitely many terms of this sequence lie outside that window. Okay. Well, I can just take the one that is furthest outside that window, make that a new radius, or tack that on to my radius, and I can gather up all of the terms in the sequence in some giant radius ball. Doesn't matter how giant it is, it's still finite. And that's exactly what's being done here. Okay. All right, so to state some more facts here, first I need a definition. This is a definition of an absolutely convergent series. So what is absolute convergence? Okay, so a series is absolutely convergent, or said to converge absolutely, if, so this series is always is the usual notation here, the sum from 1 to infinity of z sub n. So this series is absolutely convergent if the series, which is defined as the sum from 1 to infinity of the modulus of the nth terms here, okay, converges. Note, this is slightly different than the situation we had going in Calc 2, because in Calc 2, when you talked about absolute convergence, you were dealing with a series of real numbers. Okay, well, this is also a series involving each of its terms are were real numbers in both cases, right? Sorry, so when we were in Calc 2, the series we started with was a series involving only real numbers, and this absolute series also involved only real numbers. But here we have a series involving complex numbers, right, generally. And this series, even if these are complex numbers, of course, is still a series involving real numbers, right? In fact, we can actually rewrite this, right? This is the sum from n equals 1 to infinity of the square root of x sub n squared plus y sub n squared, right? And so this is now a series involving real numbers. If this thing converges, then we can say that our original complex series is absolutely convergent. Okay. Now, this was important to us because there were various theorems that we stated in Calc 2 that had implications for absolute convergence. And so an example of one of those is the following fact. So this is my fact 3. This is another corollary of that theorem. The absolute convergence of a series of complex numbers implies the regular convergence of the series. And so absolute convergence is stronger. Okay, again, note, converse isn't true. Okay, converse isn't true. So example, the alternating harmonic series. So alternating harmonic series. This thing, so minus 1 to the n over n. This thing converges. So this thing, converges. There we go. I don't know why I was writing convergence there. So this thing converges, but if I look at the absolute series involving this thing, this is the regular harmonic series. So this does not. Okay. So this thing converges by the alternating series test, okay, from Calc 2. So that thing converges, but the regular harmonic series, our favorite counterexample involving series, does not. Okay. And so, again, implying convergence doesn't imply that absolute convergence happens, but the opposite of that works, right? So if you have a series that's absolutely convergent, then it converges. This is the thing that allows us to find what's called conditional convergence. Okay, later. And so this is another nice thing that allows us to characterize what's going on here. Okay. So you can use what's called the comparison test in Calc 2, right, to actually prove this. So I'm not going to prove that corollary. Well, maybe I will. I'll say proof. Comparison test. Okay. All right. Okay. And so there's another there's another term I want to introduce, which will make our lives easier when we're talking about some of these quantities. If the sum of a given series is S, then the remainder, okay, say rho sub n, instead of the sum, of course, involves infinitely many terms in the series, but let's say we only sum up to this big N, right? Like it's a sequence of partial sums here. After only n terms is defined to be, so this rho sub n is defined to be the total sum, S, minus the partial sum, right? Thus, what we've done here is we've rewritten our total sum as the partial sum plus remainder. So this is equal to, partial sum plus remainder. So this is, I should say, total sum here on the left, right? So this is total sum. So total sum is equal to partial sum plus remainder. Here is what I've written when I write this boxed phrase. Okay. Now, since we define the convergence of a series in terms of the convergence of its sequence of partial sums here, we have shown the following fact. So fact 4 here, we can recast this as a series converges to S if and only if, right, the sequence of remainders converges to 0. And now, if you remember what it is we did in Calc 2, once we were comfortable with series, and especially once we were comfortable with power series, which are coming up here in a second, talk about remainders should immediately remind you of some particular remainders in the context of a series. And these are the ones that show up in Taylor's theorem. Okay. Okay, that was kind of, that was one of the key things that popped out of it. Okay. So this is something that we will use over and over again in that context I just mentioned when we talk about power series. So we will use this many times in our discussion of power series. So what is a power series? A power series, well, let's do it on the next page. So a power series is of the following form. So it's a sum from, well, n equals 0 to infinity, for being more general, of a sub n times z minus z naught to the n. Okay. All right. And so, what is this if I actually write this out? There's the 0th term, which is a constant term, a naught, plus a sub 1 z minus z naught to the first, plus a sub 2 times z minus z naught squared, plus a sub 3 times z minus z naught cubed, and so on. All right, so this is an infinite degree polynomial is the idea. And so power series are the natural kind of extension of polynomials, right? So polynomials are kind of like your favorite example of like everything you want in a function, right? And so you're very happy if a function you're dealing with turns out to be a polynomial, right? Well, then you encounter plenty of functions that aren't polynomials, so exponential function, sine, cosine, things like that. But of course, right, when you talk about Taylor's theorem, so when you talk about Taylor's theorem for the first time, you show that, oh, actually, yeah, they're not polynomials, but there are power series representations for those functions. And since power series are, basically polynomials with infinitely many terms, right? So they're polynomials with infinite degree. Then actually all those other really nice functions that I'm used to, while they're not finite polynomials, they are basically what we could call infinite polynomials, right? They have power series expansions. And so, basically we're happy there because we have found a way of describing in terms of them being related to polynomials in some way why they're nice, right? Okay. So when I write a power series like this, so z naught and all of the a sub n are just some complex constants. Okay. And z is any point in some region that contains this z naught. So it's any point in some region of the complex plane containing z naught. That's the context. Okay. Okay. So n for a power series these previous terms, we will use the following notation. So the previous terms will be labeled. What I mean by previous terms here are S sub n and rho sub n. These would be labeled S of z, S sub n of z, and rho sub n of z, respectively. Okay. Since they're going to depend on z. Okay. So let's use a quick example here. Okay. Which is making use of this fact that formally it is easy to write these powers, these simple powers. So let's do the sum from n equals 0 to infinity of z to the n. Okay. Let's consider this. So if I write this out, right, this is 1 plus z plus z squared plus z cubed and so on. Okay. All right. Now, if I were to look at this thing, one thing I can note here, what happens if just formally I take that expression okay, and I'm just going to pretend, right, like I can multiply it by 1 minus z. So when I say I'm doing something formally, I'm just basically applying the usual rules of algebra to some kind of like maybe, possibly not well-defined thing. I'm just trying to see what happens here when I do this. So what do I get? I get 1 times this thing. Okay, so that is 1 plus z squared plus z cubed, and so on. And then I get minus z times this thing. So what happens when I multiply minus z times this whole expression? I'm going to get minus z times 1, so that's minus z times z, which is minus z squared, minus z times z squared, which is minus z cubed, and so on. In fact, it's going to work out in such a way that all of these terms cancel, and I'm going to end up with 1. So it seems like I have suggested that 1 plus z squared plus z cubed and so on is actually equal to dividing both sides by 1 minus z here, 1 over 1 minus z. Huh? So what kind of trickery did I just do? Well, this is kind of hand-wavy in that, like, how do I know that this product of infinitely many things is something that I'm allowed to do? Is it something that I can just freely do? Well, let's actually turn this intuition for what's going on here into something that's rigorous. Okay, so then the idea is to do the following. Okay, so idea is to use that, what I just showed, to apply that to a finite sum up to the nth power. Okay, so it turns out that if I look at this thing, so up to the nth power, and I multiply, say, this by 1 minus z, what do I get? So I'm using the same idea here. So I get 1 plus z squared plus z cubed. Because this is a finite thing, I can do this. There's no problem here. Right, and then I get minus z times all this stuff. So I get minus z times 1, so that's minus z times z, that's minus z squared, minus z times z cubed, or sorry, z squared is minus z cubed, and so on. Oh, sorry, all these are minuses, all the way up to, I get minus z times z to the n plus first, which is minus z to the n, and then minus z times z to the n, that's minus z to the n plus 1, right? And so everything cancels here except these two terms. And so what I get is this is equal to 1 minus z to the n plus first, right? So then I have this identity. This is 1 minus z to the n plus first. Okay, and so dividing both sides by 1 minus z, this tells me that 1 plus z squared and so on, plus z to the n. So this finite sum is equal to 1 minus z to the n plus 1 over 1 minus z. Okay, so nothing I did here is hand wavy now because, well, these are all finite sums, so there's nothing wrong with what I'm doing. I don't have to justify being able to expand those things. Okay. Now, why does this help? Because these are partial sums here, right? And so if I look at these partial sums of that power series, right, this is the sum from n equals 0 to big N sub 1, okay, of z to the n. All right, so this is 1 plus z squared all the way up to z to the big N minus 1. Okay. All right. Now, what we want to do here, right, you might have looked at this quantity and you might say, well, I don't want z to be equal to 1 here, right? That's the only hand-wavy thing that has happened. And so if I just say z is not allowed to be 1 there, then I'm happy in that expression. Okay. So then if that's the case here, what becomes of this expression? Well, because of this identity here that I've boxed, this is really equal to 1 minus z to the big N over 1 minus z. Okay. And so, what would I... So first of all, here's my sequence of partial sums that depends on z that's given here in terms of this. What do I think S is going to be? Okay. The idea is that S of z is actually equal to 1 over 1 minus z, i.e., in this case, since we're writing this rho sub n of z to be s of z minus s sub n of z, this is z to the big N over 1 minus z. Okay. In this case, the modulus of rho sub n of z is equal to the modulus of z to the big N over the modulus of 1 minus z. So this goes to 0 if the modulus of z is strictly less than 1. Okay. But it does not tend to 0 if the modulus of z is greater than or equal to 1. Okay. So what did we show? You might recall calculations that you did in Calc 2, specifically of this type. We showed that the sum from n equals 0 to infinity of z to the n is equal to 1 over 1 minus z. That was the s of z, okay, that we got as our idea for where this was limiting to, right? Okay, from that very first thing that we did, right? So the very first thing we did was we computed this, and so this was our guess for what s was, and we found that when that was our s of z, these remainders limited to 0 in exactly the way that I need them to for this thing to converge. And so we showed that this is the case, but not always. This is only when the modulus of z is strictly less than 1. Okay. So in the terms of Calc 2 here, we found, here we could say that this function 1 over 1 minus z had a power series expansion that looked like this, and its radius of convergence is 1. Okay, and so we could only talk about this on this open ball. Okay, so that was what we did there. Now, really, that is just kind of the warm-up for the real thing that I'm interested in, which is Taylor's theorem. So I'll state Taylor's theorem, and then I will be done. So our main purpose is the following. So we have Taylor's theorem. And this is going to be phrased in a slightly different way here because we're in a slightly different setting, of course. So suppose that f is analytic throughout the disk. That is described by modulus of z minus z naught is strictly less than some r naught, okay, centered at z naught of radius r naught. Okay. Then f of z has the power series representation f of z is the sum from n equals 0 to infinity of a sub n times z minus z naught to the n, where the modulus of z minus z naught is strictly less than r naught, where these coefficients a sub n are defined to be the nth derivative of f at z naught over n factorial, where n is a whole number, so 0, 1, 2, 3, 4, and so on, i.e. the series in star converges to f of z when z is in that open disk. Okay. And so at the beginning of tomorrow's lecture, I will go over this exactly to go over exactly what this says. This finally gives us the statement that I told you about in the first week of class, where if f is analytic, it has a power series representation. This particular power series representation is called a Taylor series. Okay, and so what this is saying is that the Taylor series for this function, for an analytic function, converges to the function in this specified open disk. So this is the statement that if you have an analytic function in our complex sense, then you have an analytic function in the old sense. You might have first encountered the word analytic, which told you that you had a power series representation. So we're not misusing the word. The word means exactly the same thing in that way, that if you have an analytic function, then locally in some open disk you have power series representation for the function. All right, so I will continue on from there tomorrow. All right, so I will see you then.